Welcome to SanfordFlipMath. This is PreCalculus. We are working on polynomial functions of higher degree. We are working with the PreCalculus book from Demana, Foley, Kennedy, the 5th edition. And just to keep you on track, we are in section 2.3 of the book. And we're going to focus on basically these four things, and we'll try and keep the time under control. Polynomial in standard form. A little bit of review. Polynomial function might be y equals or f of x equals, and it's going to be some kind of coefficient, x to the n, some kind of coefficient, x to the, and all I'm doing is counting down by exponents. And keep in mind that any of these coefficients could be negative, so a could be a negative number, b could be a negative number, and this would all go all the way down to some mystery letter. I don't know, maybe we'd pick, I don't know, p, x to the 1, and q might be the last one. And I don't want to imply a certain number of terms, don't want to imply a certain exponent to start with or for degree, but this would be a polynomial function in standard form. An example might be like f of x equals 3x to the 5th minus 4x to the 3rd plus 2x plus 7, okay? So that's an example. Now obviously there are some terms missing here in terms of counting down by ones, but you can imagine a 0x to the 4th in there and a 0x squared in there, and they don't have to be represented in there, just as long as, now standard form would have them in order going down by exponent or by degree, and that's pretty much it. And you should already know that the leading term would be the term with the highest degree. And so that's the leading term. And the leading coefficient would just be the coefficient of that term. In this case, it'd be 3. Okay? Not terribly exciting, but you could have something even like 3x plus 2. And yes, that's a polynomial. Yes, it's in standard form because it's in order from in descending order, x to the 1 and then x to the 0 here, and the leading term would be 3x and the leading coefficient is 3. Okay, that's pretty much all we have to say about that. Now I want to remind you that the zeros of a function are the x values that make the function 0, that make the function equal 0, also known as x-intercepts. Okay, so they're called the zeros because they make it 0. Okay, and so if I go back and look at an equation, let's say it's something clever like x squared minus 3x plus 2. We've got lots of ways to find those zeros. Could look at a graph, could look at factoring, could do a quadratic formula, could look at a table and just kind of eyeball and see where the y values are 0. I specifically want to focus in on factoring for just a minute, and just a reminder that if that's a positive, then that tells you that these signs have to be the same. And if they are the same, then they're whatever that sign is. So this is going to be x minus and x minus, and I need factors of 2. 1 and 2, or 2 and 1, that add up to 3. Well, I guess it's something like that. Okay, so the zeros of this, the things that make the y equal 0, are the things that make these factors equal 0. So x would have to be equal to 1, and or x would have to equal 2. Those are the only two possibilities that make this equation the 0. So those are zeros. Okay. Well, similarly, if I told you the zeros, let's say I told you the zeros of some mystery function are x equals 3, x equals -1, and I asked you to build a function, build an equation. Okay, so I want a polynomial equation with those zeros. I can go backwards from what I just did. Okay, so for instance, I need x equals 2. Well, that came from x minus 2. Because I needed x minus 2 to equal 0. Well, if that's true, then I add 2 to both sides. Well, same idea here. Excuse me. If I want this thing to end up equaling 0, I'm just going to subtract 3 from both sides, and that's one of the factors. I could add 1 to both sides, so I get equals 0, and that's the other factor. Okay, or if you say a function or an equation that has those zeros, there it is. And if it specifically said standard form, yes, I can multiply that bad boy out. So x squared minus 2x minus 3, I'm just distributing or foiling or whatever way you want to refer to that. Okay, well, that's not such a big deal. But what's exciting is it could be more fun than that. So for instance, let's say we want to write a cubic with the zeros x equals 1, x equals -1, and x equals 0. Okay. So here we go. This came from the factor x minus 1. Basically, it's just opposite sign. And it's that same idea like we just saw a minute ago, where I had x equals -1, and I made that into x plus 1 by making it equal to 0. Okay, so I subtracted 1. Okay, for the next one, x minus a -1. So basically, it's always x minus the 0. So x minus a -1, well, I'm going to write x plus 1. Okay, and then I need x minus 0 for this. Now, that's not very exciting, but so you can write just x if you'd like. Okay, now this needs to be either equal to 0 or it needs to be y equals. So if it's an equation written with those zeros, then you would say equals 0. If it's a function or a graph or something like that, then it'd be y equals. Okay, the rest of it's the same process. Okay, now it could specify to write that in standard form. Now, typically what I do is I ask for it in factored form sometimes, and this is factored form, and sometimes I ask for it in standard form. Now, standard form is, as you might imagine, a lot of fun, and by a lot of fun I mean not a lot of fun. Basically, you need to multiply everything out. Okay, so I'm going to start with this. So this is x squared. Well, it's going to be plus 1x minus 1x minus 1. And those are going to go away. So x squared minus 1. And then x minus 0 is just x. So I just have one more step to go here. I'm just distributing. And there it is. So that is the equation that had those zeros in standard form. Okay. All right, so I need to up the ante one more little bit. What if I had zeros, let's say x equals 1, x equals 1, x equals 3, and what if I told you it also passed through the point 0, 5? Actually, I would prefer 0, 6. Sorry, it's easier to change it now before we do a bunch of work. Okay, so let's get a little picture of what's going on here. We actually are passing through, or we're touching at x equals 1, we're touching at x equals 3, and we're going to go through 0, 6. Okay, so I am going to give you a rough sketch of this. Well, that can't be it. I guess it can. All right, so anyway, that's a rough sketch of what we're talking about. Okay? All right, so let's do it. Well, I know one of the factors needs to be x minus 1. I know another factor needs to be x minus 1. And you guessed it, another factor has to be x minus 3. Now, the question that I have is, how does this happen? Well, it is actually going to happen by that little guy right there. Okay, let me just give you a big fat word of warning. Some people sometimes try and just tack on a 6 right here. And can I just say, that ain't it. Got all my good English grammar going. That's not it, because what that does is it shifts the entire graph up 6 units, and then this doesn't make those 0 anymore. It makes, you know, you'd have to make it somehow 6 or something. Okay, so don't do that. Instead, we have a number that can multiply out here. And if there's a number out here that multiplies to achieve that 6, then these still can equal 0 when x is 1, or x is 3. Okay, so that will actually work. So the question is, how do you find that a? Well, you just substitute in the 0 and the 6. So this is an x, this is a y, so 6 equals a times 0. I'm going to write all this out. So all I'm doing is substituting in 0. Well, all of this stuff, this is just -1 times -1 times -3. That's 3. Sorry, negative 3. And we just divide both sides by -3. A equals -2. Okay, so in factored form, this would be y equals -3, x minus 1. Now, I'm going to be a little lazy and write that in a little shorthand notation there. Okay, and then one other thing I want to do with this before I leave this, there's a term called multiplicity, which just has to do with things happening more than once. And it turns out the 0 for this equation, x equals 1, has a multiplicity of 2. So the question is why? Well, mainly because it happens twice. It counts for 2 of the zeros for this cubic equation. X equals 3 has a multiplicity of 1. And in other words, it's just accounting for a 0 one time. So that multiplicity happens in 2 spots. One, I'm listing those zeros here, and also notice that the factor appears twice. Okay, and you can do that with an exponent, or you could write it separately like this. Okay, so it's just a term that comes up. And what we'll say, now one of the things I want you to notice is look at the graph and look when it had that multiplicity of 2 there. Look how it came in and touched the axis but didn't actually cross it. If you have an even multiplicity, the graph touches the axis but it doesn't cross. It looks kind of like the vertex of a parabola there. Okay, and so to contrast that, notice that 3 had a multiplicity of 1 and it went straight through. I mean, it's on a curve, but it went directly straight through. Okay, well, just to go off on a little bit of a tangent here, if I have a graph that looks something, let's say, like this, this point right here, whatever that is going to have an even multiplicity. So let's do something like, I want to stick one more in there just so this is 4 and this is -3, just so they're not the same number. Okay. All right, so this has an even multiplicity. So this is going to come from the factor x plus 3, and it would be squared. Or it actually could even be to the 4th. Or it could even be to the 6th. Now, usually we just assume it's the smallest one that makes sense. Okay. Now, this one crosses. It doesn't just go in and touch, it crosses. So that means that we had to have an odd multiplicity. Now, there's a little catch here. Remember on this other one, it went straight through. That had multiplicity 1. This one has a little flat spot. It goes in and goes, woo, woo. Well, when it does that, it had to be an odd multiplicity, but it had to be greater than 1. So, for instance, it could have been 3 or 5 or 7. So, as I'm writing factors for this, this is probably going to be like x minus 4 to the 3rd. Can't be to the 1st because there's that little inflection there. That's the math word for that. Inflection point. But it had to be odd because it crossed. Okay, so this would be a quick little equation for this. Now, keep in mind that I don't really know what this number is, and based on that number, I could figure out what A is. Or even for any other point, I could, even if I knew this point, I could substitute in the X and the Y and solve for A. Okay, usually if we have a y-intercept, that makes it a little easier. Okay. Okay, I just want to spend just as quick as I can talking about basic shapes of graphs. And one of the things, let me point this out to you. This graph is actually a 5th degree, and I can see that by looking at, I have 1, 2, 3, 4, 5 factors that have x in it. Okay, so if I multiply this whole thing out, it's going to be a quintic function. So something x to the 5th plus something x to the 4th plus something x to the 3rd, etc. Some of those terms might be missing, but the highest degree would be 5. Okay. As I pop back here, notice this is cubic. Okay. And what I want you to notice is these shapes. Okay. So let me just kind of start a little sketch here. You already know what y equals x looks like, a 1st degree function. Okay. If I have y equals x squared, okay, so again, degree 2. In fact, let me do this just a little bit different. Okay, let me just say a degree, and then we'll do a little sketch. Okay, and we'll do this. I want to do 2 different versions of this. Okay, and so this will be the sketch. Okay, so degree. Well, let's do degree 0. So this is like an example would be y equals 2. Okay, well, there it is. That's exciting, isn't it? Degree 1, an example might be y equals 3x plus 2. Okay, it might be something like this. Okay, 1st degree did that. Okay, 2nd degree might be y equals x minus 1 squared. Let's do minus 3. Okay, so something like this. Okay, degree 3. I don't know what the equation is, but it could look like that. Could also look like this. Okay, let's do degree 4. Could look something like this, or upside down. Could also look kind of parabolish, but it would be flatter in the middle. That'd be more like a power function version of that. 5, 5th degree. Yep, something like that. Okay, again, it could be upside down. Could have fewer turns. Could even just have the inflection, and that's it. Okay. What I want to focus on is like the most extreme case because of these, because that's where it gets interesting. Okay. So 0 degree horizontal, not very exciting. 1st degree, I'm going in one direction. 2nd degree, I'm going in 1, 2 directions. Doesn't really have a corner. 3rd degree, 1, 2, 3 directions. 4th degree, 1, 2, 3, 4 directions. So I'm going like from increasing to decreasing to increasing to decreasing. That's kind of what I mean by this. I don't know what, other terminology that's not like calculus to use. 5th degree, 1, 2, 3, 4, 5. Okay, so with that in mind, 6th degree, you guessed it, 1, 2, 3, 4, 5, 6. Or it could be upside down. Now, understand that all of these things could be stretched and shifted around, so like a 6th degree could look something like this, but it's that basic idea. Okay, so here's the deal. The maximum number of directions, for lack of a better term, would be whatever the degree is. Okay, that's really useful, and also worth noting, the maximum number of real zeros is also the degree. So for instance, like this 6th degree could have 1, 2, 3, 4, 5, 6 zeros, 6 x-intercepts. This 5th degree could have 1, 2, 3, 4, 5 zeros. Now, they may not all be real though. Okay, let's pop back to 6th degree for instance. This only has 2 real zeros, and all of the other ones would be imaginary. Okay, so these guys that actually, where it actually cross, would be real. All right, I need to be done. I think we hit most of our list. Let me just kind of pop back. Zero squares. Yep, I think we're good for now. Okay, leading coefficient is just going to go to the direction. Okay, just like in a parabola, it would normally open up, and if it has a negative, it flips upside down. All right, I need to stop, and I thank you very much for being attentive, and we'll see you in class.